All right. So first of all, how do you deal with power series? What's up with that, right? So you might have heard of the geometric series, this guy over here, like this form, where this guy's a constant, this is also a constant, and this is a variable. This is X here for you guys. And for this again to be convergent, you have to be careful so that, again, the size of R is less than 1 if it is convergent, right? If it's greater than 1, the size of R, then it's going to be divergent. So here's the thing. This will come back when we're doing an interval of convergence and radius of convergence. But you start from here, okay, from this guy, and you only will work ever with this case here when you're doing power series. Obviously, we won't do a power series with an X that is violating this because the power series will diverge. It won't give anything meaningful. So we can't use power series on guys that have X's with magnitude greater than 1. Now, again, you'll see how this will change with the centering parameter as we go along. But this is your base function here, okay? This is what you will use forever. This is like the Lego block here, Kelly, that you're going to take and you're going to apply it and modify it to build other functions from it. That's exactly what's going to happen here. So let's jump right into it then. This is your building block. Let's go and see what happens on the examples that I've given you here. And then we'll talk about some more of the notes there. So this is your building block. And you're tasked right now to find the power series of this guy. First thing that you do here is realize that this can be thought of as a composition of two products here, okay? Why not split it up, since we know we're going to have to use this eventually, and this doesn't have an x to the 7 on the top. Why don't I split it up into 2 bits, and I put the x to the 7 up front, and then the 1 over 1 plus 4 x cubed on the bottom. And that way, I'm closer to the building blocks form than I was before. That's the idea, at least. So then you ask yourself, looking at only the bracket term, you go, how can I make the bottom here identical to the building block? Like, what do I have to do to this to turn it into that? What do you think I have to do to this negative x to turn it into a 4x cubed right now? What do I have to replace it by?
Multiply by negative 4x squared.
Exactly. So, you use over here, I like to write the substitution that I do like this. So my x for this guy essentially becomes negative 4x cubed. Okay. So again, I use the building block here with this substitution, okay? Because I want to express right now this guy. That's what I want to be doing. Okay. So 1 over 1 plus 4x cubed now becomes simply the sum from n equals 1 to infinity. And then you've replaced again, remember your x, wherever I see an x, I replace it with this guy. I see an x here, therefore I replace it with what you just said. And now I distribute, because this is not over yet, I distribute this in. The 4 can come all the way out to the front right now. But you have that negative 1 that will give you an alternating series all of a sudden. If you distribute the power in here to these two things, you will get a negative 1 to the n here, Kelly, and then x to the 3n, obviously. So that's actually the power series representation of this guy. You got it right here. Now, that's not what we were being asked, though. We were being asked about what is x to the 7 times this. So what do you think I need to do here to continue?
Wait, for this one, like negative 4x cubed, why is it not negative 4x squared?
Because, so when I distribute the n in, I get this, right?
No, like before the step, like the yellow step.
Yeah. Was it square? It was cubed all along, right? So our substitution is cubed.
Oh, so you just replace x.
Basically,
Okay.
yes. So whatever I see here, I replaced this x with this guy.
Okay.
Done and done. So because again, I want to use the red as a building block where I will draw basically what the new function is going to look like in the power series world. I use the base function here, which corresponds to this f of x, but I want this f of x over here. So I notice that they differ in this way. And then that's why I go back to the building block and say, all right, I'll change you to a negative 4x cubed so that you guys can match, because that's what I'm chasing after. I'm chasing to make the red equal to the white here. How do I do that? By doing the yellow substitution, basically.
Oh, okay.
So once I plug in, and I've got the power series here for that, I still have to multiply by x to the 7, right?
Yeah.
So let's do that actually. Let's multiply now by x to the 7. You'll think, okay, how will that change things? Well, when you multiply now the series by x to the 7, can't the series absorb that power of x right now? For example, can't I go and put this guy in conjunction with this guy right now? Since I'm multiplying the entire series here by this x to the 7, can't I just distribute it into the x terms that it has? I sure can. So when I do that, I'm left with this 4 sitting on the outside, then the negative 1 to the n, and then what happens to the power of x?
Becomes 21.
Not 21, now we're going to add the powers. We're multiplying x to the 7 with x to the 3 to the n.
Oh, so 10n.
Close. That doesn't have an n on it, so it would be 3n plus 7 rather. It didn't have an n attached to it, that x over there. So we literally add the powers together. So 3n that was inside, and then plus the 7 that's sitting on the outside right now. And that is the end. That is how quickly you can get the representation. Okay. I'll put that over here so that you can see it.
Mm-hmm.
That's it. Now, another one that's really interesting to look at while we're at it, let's look at lawn over here. Okay, really quickly, because that's another one they might want you to work on. Actually, either one of these is good.
Mm-hmm.
Now, tell me something you know. Well, does this look anything right now to you, Kelly? Does this look anything like the red?
No.
Okay. Is there, though, a clever way that we can make it look like the red? And it involves either integration or differentiation. What do you think?
You derive the lawn.
If you do take the derivative, right, what do you get?
1 over 1 minus x.
Don't forget, though, the inside. What do you get from the inside?
Minus 1.
Mm-hmm. So you get this, and take a look at this again. Look how similar these are, right?
Yeah.
So the idea here, Kelly, is why don't I find that the power series representation of the derivative and then integrate that to go back to f of x and find that power series. You know what I mean? That is perfectly doable. And that's exactly what we're going to do here. So you might be wondering, how do I do this right now? Well, having the negative here corresponds really to this, right? Like it's literally the same thing. If I write the derivative like this, it's literally the same thing.
Yeah.
Another way we can think about it is factoring out a negative, right? So, we're wondering again, what could we do here? Let me write it like this, actually. So negative here 1 minus x. I just want to keep it like that. Okay, so we have a negative, and we're trying right now to think how we can combine these together, right? Think about this for a second. So what could I do here? What could I do to this x, or to the whole power series itself? What could I do to mimic? I want to match, let me explain. I want to match this to this right now. What change do I need to make to the red?
Multiply by -1.
That's it, right? Literally, I don't even have to write this step. That's it. So we take this guy and we go, all right, -1 over 1 minus x corresponds to literally having the negative of the series. And you'll see that negative right now, I'm not putting it in the series. That's not going to make the series alternating. We literally multiply here both sides by -1. And that's it. So I'm not there yet. I'm not there yet because let's think about this. That is not ln of 1 minus x, right? That's definitely not that. However, I can do integration here, Kelly, right? And integrate this function and integrate that guy over here as well. And you might be wondering again, how do you integrate a sum like this? Well, it's the same deal as you would integrate a normal function. So I would distribute the integral inside the sum because, again, this integral is related to x. It has nothing to do with the summation here. We can distribute it in here and write it like this, okay? So this is nothing more than a polynomial getting integrated inside that sum. What would the result be here?
X to the power of n plus 1 over n plus 1.
Exactly. That is literally it. And so on the left here, though, when we integrate this, what do we expect to find?
Ln of 1 minus x.
Yep. And the negative here gets absorbed because, again, we are literally, this negative is needed to get absorbed because when we write down ln of 1 minus x again and differentiate it, there's that negative that pops out, but we don't want that negative. So that's why this gets absorbed when we do the result here. Okay. So you see again that we literally just finished getting the power series of ln of 1 minus x. That's it. In a similar way, I'm not going to do this one because you want to leave a little earlier. So try here, remembering that the derivative of tangent is 1 over 1 plus x squared, like that. Not tangent, excuse me, arctangent. That's its derivative. And try to think again how to use the building block. This will be your homework. Try to think how to use this guy to get the derivative and then integrate the series that you got to get the original that you are interested in, okay?
Okay.
Moving on, though. Okay, so that's also, again, one that you can do easily over here through integration. So I'm going to leave these two as homework. I got to cover a lot of stuff. Okay. So determine the radius and interval of convergence. All right. How do we do that? Again, where is it based on? It's based on what I told you originally for power series. That argument here, this x plus 4, this thing right here, it better overall be, again, its size better be less than 1. Like, that's what we care about. And it's because, you know, for this series here to converge right now, Kelly, we need the ratio test to succeed. We need the ratio test to tell us that it actually converges. Let me explain a little bit better. On the note, when we go back here, you will see the following. when we talk about radius of convergence, okay, we want this is the ratio test basically. If you read the notes, this is what the ratio test is. You take the inside part of the series right now, add 1 to the n terms, and then divide by the original a sub n. So we want this to converge to some value L. And if you remember, okay, if you remember from the notes here, let me show you on the ratio test 1 sec. When you do the ratio test, for me, these were P's on that note, but whatever, it means the same thing. When you do the ratio test and take this limit, watch what happens. If the limit turns out to be greater than 1, then we diverge. We don't want that if we're expressing a function as a power series. Neither do we want it to be equal to 1. So we want the ratio test, when we take the limit of this r, to be less than 1. That is guaranteed. That's what we want when we're doing power series. So going back to your power series notes, we are setting ourselves up so that this limit equals L, and this L is, again, less than 1. That's what we want to find. So we ask right now, okay? We go, all right, if this L is to be less than 1, what can I make right now this left-hand side equal to? Okay? What values? Yeah?
So it has to be 0?
No, not necessarily. Not necessarily. So it has to be less than 1, between 0 and 1, and that means your power series converges. The ratio test succeeds, and it tells you that the power series converges.
What does like converges or like diverge means?
The difference is that if it converges, the series ends up being a single value, right? A very single, non-infinite value. It's a finite value. The whole series ends up giving you a number. But if it diverges, it gives you infinity.
Oh, okay.
So the problem, of course, is, we want to find exactly for what values of x our series will converge. And you said, George, you said over here, like if this x is smaller than 1, then you converge. Yes, I know I said that. But this was for this simple power series right here. This was only for this guy. As soon as you start modifying this, Kelly, the criterion here changes. For example, if I go right now and add to the x a 1, and I have x plus 1 to the n, this criterion here will change. In fact, what you are looking for here, again, remember, this is the geometric series. What you're looking in the yellow part here, that is the radius of convergence of the geometric series right now. That's what you're looking at in the yellow bracket. So it is 1. Your geometric series has a radius of convergence of 1. And it's centered at 0. Why, you might say, it's centered at 0? I'll explain one thing at a time. So there's a thing called the centering parameter, and I want to find where I have a note on that right now to tell you. I have a note on the Taylor series. Okay. Ignore the fact that we're doing Taylor series on the note. I just want to show you, what's Taylor series? It's another kind of power series. Really, that's all there is to it. Okay. And these constants are those fancy derivatives that you take. Like, again, you'll see here. Those are the constants. They're just fancy derivatives evaluated at the centering parameter. So what's the centering parameter, you might say? This guy over here, this A. Remember I said the simple power series again, Kelly, is this, right? That's what we were investigating so far. But I said, I can modify this. I can add or subtract things on the x, right? I can multiply the x by things like constants, right? And those affect now the values of x that we will converge at. So instead of converging now with a radius of 1, they will that one. They will alter it. As soon as you start modifying here, you add or subtract numbers, you multiply, you're changing the values of x that you will converge at now. That's the idea. So instead of having a radius of convergence of 1, you might make it bigger or make it smaller, depending again on what these modifications are. So again, a Taylor series is just a fancy power series. That's all there is to it, okay? And this guy controls where you center the power series. It's like transformations for functions from back in like grade 10. When you removed a constant from your function, it corresponded to a horizontal shift to the right, to the right. And if you added a constant, it corresponded to a horizontal shift to the left, right? That's what you did in transformations for functions. When you multiplied a function by a constant, it either, again, depending on the value of this, it either stretched the function vertically or it compressed it vertically, depending if this was greater or smaller than 1. And that's exactly what's happening here. Really, this stretches the actual radius of convergence or compresses it, and this shifts it. This shifts the interval of convergence from 0 around. So I want you to think about the whole topic here in the form of a circle, okay? And I'll explain again really quickly what the hell am I talking about. I want you to think about it like this. So get rid of the stuff that doesn't matter. Okay, so when you're doing the original power series that we were doing before, like the x to the n, right? When we're doing this guy, we said that he converges if x is less than 1. Okay, this is a must. Now, the centering parameter of this one, you can very well see what it is. Okay, we don't have any a right now. This a is gone. So the centering parameter is 0. It means that this circle for the values of x that we converge is centered at the origin right now. And I said my radius of convergence is just 1. So you can think of this radius right here of this circle as 1. That's it. Now I know that this is not really two-dimensional, this problem. This is one-dimensional. And really what you're talking about is how wide this line can be right now, right, on either direction. It's not really two-dimensional. We're only worrying about values of x. There's no other variable that we're doing here. I think the circle, though, works in a better way visually for you to remember what we're talking about, that it's a radius that you're trying to find. It's like, how big is this right now? We're saying that it's equal to 1 because, again, by definition, for the ratio test on the geometric series, that's what it needs to be. So it's 1 right now. And I like to leave the circle like this, even though, again, we're not ever touching the y-axis. We're not even worrying about that. We're only worrying about what's going on along this line. So this circle for the original power series that you used just now in the previous problem, for the original power series, the centering parameter is 0. That's why we're centered at 0. And then the radius here is 1. That's why you see that orange line have a length of 1 right now. So how do you get the interval of convergence, right? You must do this. And it gets a little trickier than this as well. I'll explain. So this is the actual interval of convergence, but Kelly, there is a chance that we also converge on the endpoints. What I mean is this here could be a value that your series also converges at, and so could this. So there's times where we have this instead, and this matters. You will lose marks if you negate this. So how do I actually find out if I converge at the endpoints? Well, you have to take the endpoints, put them into your series, and then do a series test to see if you converge or not. All this might sound like a lot, but it will make sense as soon as I do the example that I've provided. So you have to individually check the endpoints inside the series to see if the series converges at those endpoints or not. If it doesn't converge, you don't include this. If it does converge, you do include the equal sign. It is that simple once you get it going. So with that being said right now, okay, let's start investigating the example I've provided. I have two here. Maybe I'll leave one as homework, but I'll pick one. Let's do the long one. Okay. Take a look at this power series, okay? What is the centering parameter here, Kelly? What would you say is the value of A right now?
2.
It's 2, which again, if we were drawing the plot here real quick, okay, that means that our circle is centered now at 2. So it's centered out here at the value of 2. And now we're looking for the radius. Well, how do we find the radius? There is a shortcut that you can do to find the radius because it's based on the ratio test. I can show you the shortcut. I think that you should just do the shortcut all the time. But just know that all you would need to do if you weren't doing the shortcut, you'd have to do the ratio test on this guy. And eventually, again, I'll show you on the notes as I go along. Okay, so you'd have to do the ratio test. You're going to get a value, but the actual radius of convergence will be 1 over the limit that you're doing right now. Okay. In order to not get confused, I made a shortcut for this. All you really need to do here, since the radius of convergence is going to be the inverse of that limit, why not start by taking the limit inverted anyways? So instead of doing Pn over Pn plus 1, I said, just go for L immediately and just do this over this. You know what I mean? Just go for it immediately so you don't get confused. And that's exactly what you'll see me do here. I do the Cn over Cn plus 1. That's it. And I say that the pink here that you see is my radius of convergence. X must be less than that. So let me steal it, because that's literally what we're going to do here to find that radius of convergence. So that's what I want to do. All right, let's do it. So again, this radius of convergence, okay, this R, is equal to the limit as n goes to infinity, absolute value of x minus 2 to the n. Again, I need to be careful to show you. Hold on. Because I almost fell for it myself. You're going to fall for it too. What exactly is this again? This is the constant part of the series that depends on n. Think about that for a second. The constant part of the series. Is this a constant? Is x fixed, or can we vary x?
X is fixed.
Is it? Because that's a variable. We can vary that, right? To whatever value we please right now. That's what it stands for. It's a placeholder for a number of whatever we please. So that's actually not a constant. So think of the series always, right now, if it makes sense, think of the series as being of this form. Some constant and then x minus a to the n power. Think of it that way. You'll never get it wrong on what's constant and what's not, right? Because that's basically how power series are written.
Mm-hmm.
And now you can see it clearly that the constant actually is what?
Ln of n.
Ln of n, or 1 over ln of n, right?
Mm-hmm.
So again, make the identification, maybe in the beginning here, and then go ham and actually solve the problem. So I'm going to take the limit 1 over ln of n, okay, divided by this. Well, since we're dividing, why not multiply by the inverse, right? So I'm going to multiply here by ln of n plus 1. That's what I'm going to do.
Mm-hmm.
Fair enough. So in the next step, I still have the absolute values in place, but I'm going to ask you if they're needed. Let's think about this for a second. So n is always here greater than 2. It's greater than 2. I don't know about you, but ln of 2 plus 1 and ln of 2, aren't these greater than 0?
Yeah.
Okay. So even at the lowest value of n, which is 2 right now, this quantity is positive, even at the lowest value of n. And as you pump up the n, we know very well, if this becomes 10 now, those are always going to be bigger positives now. This is going to be a bigger positive, making this an overall bigger positive. We're never, ever going to get a negative from these two expressions. Are the absolute values needed then?
No.
That's how we decide to drop them, okay? Just so you know about that little note on the side. That's how we decide to drop them. So you're dealing with this limit here, Kelly. If I plug in infinity right now, I just want to let you know that what I get is infinity over infinity right now. Is this a special form in limits where I can use a special rule, someone's rule, for solving this kind of limit?
Yeah.
Whose rule?
L'Hopital rule.
What do we do in L'Hopital's rule?
You derive the term.
Yep, the numerator and the denominator separately.
Yeah.
What's the derivative of the numerator?
1 over n plus 1.
And what about the denominator?
1 over n.
Good. So overall, you get, again, if we do this, you can see we get here n over n plus 1 if I rearrange this.
Yeah.
Okay. So what is this limit now? Could we do a trick here and evaluate this?
It will still be infinity over infinity. So you have to do the L'Hopital rule again.
I guess you could. I don't know if it's going to work that well. I haven't tried it, to be honest. When I see this, you know what I do here, Kelly? I pull the largest factor of n outside both numerator and denominator. So I go and pull outside right now this. What is there going to be left inside if I actually do this?
1 over 1. 1 plus 1.
What about this guy?
And 1 over n.
Good. So notice again that these go away. And if you plug infinity now into the remaining part, which is this, what does this become?
0.
So what does your limit give you?
1.
1. There you go. So our radius of convergence is 1. Okay. So there we go. We can draw it in if you want, but now you know what you're doing. Okay. What about the interval of convergence. We said it's going to be, again, we have to be careful, the centering parameter minus this radius, and then the centering parameter plus this radius. And that's going to be our interval of convergence. So A used to be 2.
It will be 1 smaller than x smaller than 3.
Mm-hmm. That's exactly what's going on. So you get 1x3. But again, what did I tell you? We got to check the endpoints right now to see if we still converge there. So again, we're checking here the endpoints. That's what's going on in the next bit. All right. So what was our series again? It was this bad boy up here. Bring him down. Okay. And now we're going to check the endpoint. So we're going to plug in, for one here, we're going to plug in x equals 1. And then another case here, we're going to do x equals 3 and see what happens. If I plug in x equals 1, what do I get now in the series?
-1 to the power of n over ln of n.
Okay. And this is what kind of series if it has the -1 to the n?
Taylor?
Alternating, right?
Oh,
Alternating. Has positive, negative, positive, negative, positive, negative, right?
oh, yeah.
Okay. I haven't yet talked about the flow chart over here. Okay. Let me, I guess, go here and show you. But the first thing you should do when dealing with this is always check to see for absolute convergence. So instead of working on this, always check this first. Fair enough. So you go back here and you're like, all right, n right now is -1 to the n over ln of n. The absolute value of this would be what here, Kelly, if I took the absolute value of this?
Absolute of the -1 n over ln n.
That's the original. Well, think about it this way. If I took the absolute value, would I ever care about -1?
No.
No, because every time the -1 would pop up, let's say if you had here 3, every time the -1 would pop up, the absolute value would kill it. You see what I'm saying?
Yeah.
So I'd never have to worry about the -1, which means I can negate it. I can completely ignore it right now. You see that?
Yeah.
Okay. So we have to check right now if this series is convergent or not. Okay?
Mm-hmm.
So what do we have in our hands? We have 1 over ln of n. Okay. And n again, remember, is like greater than 2. Now, I have to check. And I'm thinking, a similar series here. I'm skipping again the flow chart for now, but I've done this in my head really quickly. The divergence test will be inconclusive here because it's going to give you 0. This is not easily integrable. It's not a p-series, obviously. So I've skipped the first 3 steps on the flow chart, and I'm looking immediately to do a comparison test. So what is this similar to? What other series, a simpler one preferably, looks like this? Think. What other series looks like this?
Is it the power series that we just worked on?
The x to the n.
Not sure.
Okay, I'll help you out a little bit, Kelly. So 1 over ln to the n, right? Another one that looks similar to this, and it's simpler to work with, is 1 over n. Okay? And I want you to think about these for a second. 1 over n and 1 over ln of n. And I just want you to make a quick table in your head. Usually I do this, again, in my head. But again, you can do this like this. No, nobody's going to bat an eye. I'm just really wanting to see if the series I came up with is a smaller or a bigger series than the one I had in my hands. If I plug 2 right now to this one, I get 1/2, right?
Mm-hmm.
What about the other one? Well, again, if I do 1 over here ln of 2, I get 1.44. Okay, so this is like 0.5, and the other one is 1.44. And then if I plug in 3, let's see what happens, right? I get here 1/3, which is like 0.33. And then for the other one, I get 1 over ln 3, which is 0.91. And so on and so forth, right?
Mm-hmm.
All right, so the higher I go, clearly these die off, right? So I can do right now 1 over 100, okay? Let's see what happens there. So again, I would get here simply 0.01, but for the other one, 1 over ln 100 would be 0.21. Okay, and I can do 1 million if you want to, but I think you get the point. Which one's the bigger series right now? As I go and do this right now, which one is?
Oh, 1 over ln n.
So again, I'm going to do this last one here for you as well. Ln of 1 exponent 6. That's going to be 0.07. And you can see again that at any value of n I try, that is always bigger. You see that? So 1 over n is the smaller series, correct?
Yeah.
But 1 over n, this series here that we've picked, right? This is the harmonic series. Or another way to think about it, it is a p-series with a p-value equal to what? Let's see also what you know. What is the p-value here, or the exponent of n?
1.
1. Do you remember what that means? Is this going to diverge or converge right now if it's equal to 1? If p is equal to 1 here, Kelly. If p is equal to 1,
Diverge.
Exactly. So when we go back here, all right, we understand p is equal to 1, therefore this diverges. All right. And again, since this series, right, since this series is smaller than the one that we're interested in, it's smaller than the 1 over ln of n, all right? And this one diverges, it's smaller and it diverges, right? Well, the other one that's bigger is also going to diverge.
Yeah.
So x equals, what were we trying? X equals 1 means divergence. So we don't include it in the interval of convergence. We don't include it, right? Because it's going to cause divergence if we put in a value of x equals 1.
Yeah.
What about 3 though? Let's check 3 out. Maybe something.
It'll be 1 to the power of n over ln n. So the absolute of n will be 1 over ln n.
So it's going to be, again, as you said, we will have 3 minus 2 here. So it's going to be 1 to the n, or just 1.
Yeah.
It's not an alternating series, but it's still the same series. Okay.
Mm-hmm.
an is 1 over ln of n, but the absolute value is still also the same.
Yeah.
Why? Because n is greater than 2, and any value you put here that is 2 or greater will always yield you a positive. So really, this is the same as if you took its absolute value. And so with the same steps, we've proven again, and you can look over here now. We've proven again with the same steps that it diverges, right? So we can claim over here again, x equals 3 also makes this diverge. So our conclusion is that the interval of convergence is going to be between 1 and 3, not including 1 or 3. You see that?
Mm-hmm. Yeah.
And that you have to do in every single one of these. So we got the radius up there. Okay, the radius was simple. But then to do the interval, we found a primitive interval if you must. And then we checked the endpoints to see if they cause divergence or not. If they cause divergence, they're not included in the interval. If they cause convergence, they are included. Both of our endpoints here caused divergence. Therefore, they're not included in the interval.
Okay.
And that's how you deal with radius and interval of convergence. Every single example is like this. Every single one. Like, you know, if we're to look at the other one over here, for example, what's the A value here? Just to get you started, what's the A value? Be careful.
-4.
-4. And Cn right now would be what for you?
1 over n squared times 2 to the power of n.
Perfect. So again, to find the radius, you would need to do this limit again. Okay, Cn
plus 1.
Yeah, so you'd have to do this limit, okay?
Mm-hmm.
For the sake of time, again, I want to leave that to you.
Mm-hmm.
You have to go at 5:15. I'm not going to reach to do everything else that you need, right?
Yeah.
Okay, so again, this is what you want to be doing here, the radius like this, and then you'll get the interval. Don't forget, by taking your centering parameter and removing the radius, and then the centering parameter and adding the radius. And then you got to check if these are equal signs here or not. You have to check the endpoints. Okay. That's it. So every single power series that they ask you for the interval and the radius, it's the same procedure again and again. All right?
Okay.
All right, Kelly. So for Taylor series, I really hope I get this example down in time.
Oh,
And
this
then,
one, I get this one. You can skip this one.
do you get how to use the error equation?
Yeah.
Okay. Let's get some practice then in with these guys. All right. So I pick here, if I were you, pick one that you like here, that you want to work on. One that's not obvious to you.
K.
Okay. All right.
Yeah.
So K here says -1 to the n plus 1. Okay. And we're multiplying by e to the 1 over n, and then dividing by n. And our series is going from 1 to infinity. All right. Now, again, I have a flow chart that I encourage you to use, at least to learn the ropes here of how to deal with these questions. So let's pretend I'm using the sheet. I don't know what I'm doing, okay? And I'm going to use the actual flow chart. What does the first step say?
Check for absolute convergence first. Instead of working on AN, work on absolute AN.
So what changes here if, because my AN is the whole inside part, what's the absolute value of that?
1 to the power of n plus 1 times,
Do we even have to care about that though?
no, because that one is positive.
That's always going to be a 1. So really, it's just the second part, Kelly.
Oh, okay.
Now, we hope that we get absolute convergence here when we do this, because it's going to cut our work short. But if we don't, again, we have to check anyways for absolute convergence eventually. So might as well do it right now. Okay, that is the series that you're working with right now. Let's take a look again at the flow chart. All right, I'm gonna move this with us just to show you how powerful this is. So again, I'm gonna paste it here, and what I want you to do is answer the questions that you see. Okay. Is the whole series, like this whole thing, raised to some weird power of n? Do you see brackets again? Do you see brackets and maybe like 3n here? Do you see that?
Oh, no.
No. All right. We're moving to the right. Is this a p series? So 1 over n squared, 1 over n cubed, 1 over n, 5 over n squared, 20 over n cubed.
Yeah.
Is it a p series?
Yes, because there's something over n.
But that's also raised to n power. If this was missing, then yes. Then yes, that would be a p series because that's a constant. However, that is also there, so it's not a p series.
Okay.
Moving on. Can we easily find the limit of this with n going to infinity right now? We can try. Another way to write this would be 1 over n, and then again, let's think about it for a second. If I took n to infinity right now, on the top I get e to the 0, and on the bottom I get infinity. That's 1 over infinity, which equals 0. If you do that, so we answered yes here. It's easy to get the limit. And what is the limit?
0.
0. So we're moving on to the right. We're actually not going down here.
Yeah.
So unfortunately, that was inconclusive, the divergence test. So I'm here now. Is it a product of powers of n or factorials? So do you see stuff like this? Hold on, let me do this. You see stuff like this?
No.
Okay. Is it easily integrable?
Not really.
You see, I have an option here that says maybe, right? And I'll tell you why. Because you might not be sure when you look at this, right, immediately if it's easily integrable, right? So I leave you the option of saying maybe, okay? And that eventually, if everything else fails here, Kelly, you'll see that in the very end, I say, take another shot at the integral test and the comparison test, because the integral might actually have been doable and you thought that it wasn't. So take another look at the integral and see if it actually is doable, right? I'm about to do that at the very end. All right, so we go here, we go, yeah, I don't know, maybe, you know. So I'm going to move along the right here. I'm not going to try and integrate it yet, okay? But it might turn out that we need to. I'm just saying, be aware. So what is your hunch about this right now? That it converges or it diverges? You have to think a little bit about what you believe this is going to do. I have an exponential that is decaying right now with n, and it's decaying. It's going towards 0. And then on
Mhm.
top of that, I'm also dividing by a number that's growing. I have a
Uh,
numerator that's dying and a denominator that's growing.
converges.
So my hunch is that it converges. All right. Can you come up with another series that is larger right now, let's say, than this? Think about this. What is the maximum value? Here, let me help you because I know what's going to be right here. I can see it now. What's the largest value that this will ever be? For what n is this going to give the largest value ever in its life?
1.
1, right? Because you plug in 1, look what happens. You get e to the 1 over 1, which is just e. Okay. Then as soon as you go to 2, right, you get square root of e over 2.
Mm-hmm.
Okay. Can we come up with another series? This is the hard part. Comparison test is always hard. Can you come up with another series that is now taking advantage of what you just told me? So hold on. Let me go. We need some space for that. Hold on. Let's not ruin the chart, but we need some space for that. Remember, like we had the little table over there? And I was like, okay, you got e to the 1 over n. And if you plug in n equals 1 and n equals 2, you get here e root e over 2, which again, I would like to give as a number. Root of e. Whoops. Okay, let me just do it by hand. Root of 2.71 divided by 2. All right. That's around 2.71. That's around 0.823, I guess. So what I want is another series here that is larger than this. Larger than this. Well, the maximum value that this can go is 1, you said. Max is 1. So do you know what that means here, Kelly? Like it means that if you replace this with 1, this is always going to be smaller than you. Think about it. If I replaced it right now with 1 over n, I mean, if you don't believe me, you can do the numbers, right? This is going to be now 1,
Mm-hmm.
and this is now going to be 0.5, right?
Mm-hmm.
And you can go and check if I'm being truthful. Check at 100, for example. You get here e to the 1 over 100 divided by 100. You get here around 0.0101, and 1 over 100 would just be 0.01. You see what I mean? They are always, you always have this to be greater than the other one over here. So by looking at this max value, I'm explaining you the logic here, occurs at n equals 1 and is 1.
Oh, okay.
So you replace the e to the 1 over n. You go, why don't I replace that with the 1? That will guarantee right now, I will guarantee forever that my, the left one is always bigger. That's what I did here. You can also replace it with e if you want the opposite effect. Okay, I'll explain. Let me make sure I haven't made a mistake though here. So again, the maximal value occurs at n equals 1, exactly, and is not 1, excuse me, it is e. Okay, and is e. So I could choose here to do, if I want to have a series that is larger, I want to guess a series that is larger than the original, I can use that maximum, that constant right now. in here, right? I can use that E in here. And when n is equal to 1, they are exactly equal, okay? But when n is equal to 2, we get E here divided by 2. That's 1.35. Look what's happening here. Hold on, let me explain what happened. You get here 1.35 now. 9, I guess. And then when you get the 100, and excuse me, you get 0.027. Notice again who is the bigger person here. Okay, notice which is the bigger series. It's always this. And if you can go to infinity now, if you want, you can go all the way down to infinity here, try values of n that are very large, you'll see that this relationship is maintained forever. Okay, so we're almost there. Let's see with a comparison test. So let's talk then about this series. Let's talk about this series. I can immediately factor the E outside. And I got here the 1 over n again, the 1 over n series. Does this converge or diverge?
Diverge.
Okay, so this diverges. However, it was larger than this guy, all right? And that means we are inconclusive. It's larger than our original, okay? So this is inconclusive. Let me explain why again. This series is larger than this one, and we prove that it diverges. That tells us nothing right now. If it was the other way around, then this would diverge as well. But we just proved that something bigger than us diverges. Well, that doesn't mean much. But if we prove that something smaller than us diverges, then that would mean something. So this was inconclusive. However, look at the flow chart again. So we can come up with a BN that is larger. Yes. Does your BN converge? Okay. We said no. So the no drives us here. Can you come up with a BN that is smaller than A sub n? Can we do that?
Yeah.
This is really cool. You picked a good example. Okay. So again, we're doing the table, and I'm asking myself right now, can I come up with a series that is constantly smaller? So instead of asking the max, why don't you try asking the min that this can be? What is the minimum value that the numerator can have?
0.
What happens if you drive this to infinity? What happens to the numerator, Kelly?
Becomes 1.
You said it, okay? So we're looking at this, and if we pump n to infinity, we get that the numerator is 1. So guess what? Instead of E here, what do you want to put to be consistently smaller?
1.
1. Am I saying the truth? Well, 1 over 1 is 1 right now. 1 over 2 is 0.5. 1 over 100 is 0.01. You notice that these have flipped. You see?
Yeah.
Okay, so you found a series that is consistently smaller right now. So talk to me a little bit about this series. What does it do?
So 1 over n will be diverge. And
Good.
this is smaller than the original function, so it also means that the original function is diverged too.
Exactly. Good stuff. So this means that this also diverges. All right. So what we've done now is shown that we're not absolutely convergent. Okay. So you're done the very difficult part, okay, which was finding a proper comparison test to do this. So again, we walked over here. Let me show you. Can you come up with a BN that is smaller? Yes. Did it diverge? Yes. Was the original series alternating though? Remember we had the -1?
Yeah.
So it was alternating, right?
Yeah.
All right. What do we need to do next?
The alternating series test.
Okay. So again, we need to ensure. Come on, OneNote. What happened here? I didn't want to do that. I wanted to copy it here. Okay. So the original series, again, was this bad boy. Okay. So we want to see right now if these two criteria hold up. Let's see for this guy right here. Do these two criteria hold up? Is it decreasing? Is A sub n decreasing? A sub n, again, I have to be careful here.
Yeah.
So A sub n is, again, I should call this something else on my note because it refers again to this part, okay? Not the alternating series part when you do the test.
Mm-hmm.
So I might refer to it as Cn. I don't know, I'll see. I'll find a good name for it. But we're looking at this bit of it, of the series. All right, and we're asking if it's consistently decreasing, right?
Mm-hmm.
Yes. We can test that by doing values, or a better way would be to take its derivative.
Mm-hmm.
Think of this as n to the -1 power multiplying e to the n to the -1 power. Can you differentiate this for me, Kelly? It's a little hard.
Yeah.
It's a product rule.
Negative n to the power of -2 times e n -1 plus n to the power of -1 times e negative n to the power of -2.
Okay, so the e remains unchanged as we take its derivative, right?
Yeah.
But then you take the derivative of this, and it is a negative n to the -2.
Oh, okay.
We take the derivative of the inside too. So I can factor outside right now negative n to the -2, and also e to the e to the n to the -1. Inside I got, for the first term, 1, and for the second term, just n to the -1. And if I do just write it a little bit more pretty, I have e to the 1 over n squared in the negative here. That is this part.
Mm-hmm.
And then inside I got 1 plus 1 over n. What do you notice, Kelly?
It's negative, decreasing.
So our rate of change, remember, n is always greater than 1. So our rate of change is always less than 0.
Mm-hmm.
The slopes of this function are always negative, which means monotonically decreasing. That's what it means. We're always decreasing. So we proved the first part, that we're monotonically decreasing forever. Like this function basically goes like this, right? Forever. And what about the second part? That's like part number 1. What about the second part? We have to take the limit, right?
Yeah.
Let's do it. Limit as n goes to infinity of e to the 1 over n over n. If you were to directly plug in the limit right now, you would get what?
1 over infinity. So like 1/0.
All right, so we get e to the 0 over basically infinity, and that gets you basically 0. We don't have to do L'Hopital's rule, anything fancy. So
Yeah.
we also succeed in the second test, and that means our conclusion right now is that we are conditionally convergent. Conditionally convergent. We passed the alternating series test. And again, you'll see on my flow chart. Do we pass these criteria? Yes, conditionally convergent.
Okay.
Again, you picked one that had a little bit of everything, right? It failed basically the main body of the flow chart here, which is nice. It failed like this part because we ended up here, and then it was a yes on this question. So we had to go all the way here and do the alternating series test on top of that. And then we got that it converges, so it's conditionally convergent. And that's it for that problem. So I showed you a fail over here where, again, I was looking for a series that was larger and I got an inconclusive answer from that. But then when I looked for a series that was smaller, right, I got a conclusive answer. So I got that the absolute value of a sub n does diverge indeed. Now we have to go back and do the original a sub n. If somehow we in this box here we had that it converges, we wouldn't have to do this work. You see what I'm saying?
Yeah.
But unfortunately, we did. Okay, so that's again the flow chart here. You can try it. I'm not going to keep you longer if you have to go here, Kelly. But that's again the flow chart, and the questions that we answered, I'll put them right beside here. And we got conditionally convergent for that one. Okay, questions on it? It's a little confusing for sure. It's not very straightforward, but the flow chart, I feel, makes things a lot easier.
Yeah.
So I'll copy that into the questions here. Okay, so that's the one you picked to do. All right, any questions on it?
No, I think I get it now. It's much more clear.
Okay, follow the flow chart. Honestly, like I took a lot of time to actually think of good questions to ask, and a lot of questions I saw, basically, again, how you started was always with absolute convergence. Sometimes it might be a waste of time. You might think, you know what? Why am I checking for absolute convergence when I don't even know if the series itself converges or not? Here's the thing. Let's say you did it this way first. You went and checked the alternating series and checked to see what a sub n does. And you got the fact right now that it actually converges because it passed both of these tests. So you got the fact that this converges, right?
Yeah.
Well, now you have to check if it absolutely converges now anyways. You see what I'm saying?
Yeah.
Because you have to tell your prof if it absolutely converges or not. So you have to do this work anyways in this problem. However, the only time where you would do a little bit of extra work is if this failed. If this failed and you got that it diverged, obviously it won't absolutely converge, right? You failed the alternating series test, immediately, you can say that it diverges. So, but it's safer, in my opinion, to always start with checking the absolute convergence. It's safer. Even if we have to do a little bit of extra work, it's safer. I've seen it more often than not become a disaster when you start the other way around and you check like convergence versus divergence instead of absolute convergence versus divergence. I feel like it causes, again, with the problems that I've seen, I feel that it causes more of a problem when you go the other way around.
Yeah.
Because this is set. Like once you find here that it doesn't absolutely converge, Do the alternating series test if you even have to, Kelly. If you even have to, because you might not have to do the alternating series test, because if we answered no on this question, if we answered no, it's just divergent.
Mm-hmm.
So it's only the alternating series that really cause a problem here, right? So if you had a series like 1 over 3n plus 1, right? That is not an alternating series. And once you proved if it converges or diverges, you've checked absolute convergence at the same time.
Yeah.
I'd love to show you more problems. However, again, this is not a topic that you can squeeze in an hour, okay? I will tell you that much. And I hope the flowchart helps. Give it a look. Try the questions that I have here. They're from Math 119 itself, okay? From an older term.
Oh, okay.
Give them a shot and follow the flowchart. See what happens.
Okay. Thank you.
No problem, Kelly. Let me stop then the recording right here.